Okay, example 2. Determine whether this function is a continuous at x equal to 1. Okay, so if I were you, I will graph it first. So if you graph it using graphing calculator or computer, you get graph something like this. And the question was an x equal to 1. So when I look at x equal to 1, x equal to 1 is somewhere over here. Looks like that's where this connection is. You can see 1 right here. This end keeps going up, this end keeps going down. So you should know it's discontinuous. Not only that, when you look at it, what kind of discontinuity? There are 3 different kinds of discontinuity. You should know it's an infinite discontinuity right there, just by looking at the graph. So you got pretty good idea what it is. So you can, just looking at the graph, you already got the answer. Okay, justify using continuity test. Okay, that's something you have to do. What was the continuity test again? Function exists, limit exists, function value, limit value should match. Okay, so first thing, function exists at x equal to 1. What does that mean? Plug it in 1 for x. What happened? If you plug it in 1 for x, you get 1 minus 1, you get 0 as a denominator, busted right there. So first condition, f of 1 does not exist. Done. Discontinuous. It fails a continuity test. We say continuity test, it fails the first condition, does not exist, done deal. So you say does not exist. No, not does not exist. You say discontinuous. Discontinuous at x equal to 1. So justify using a continuity test. This is what I meant by that. Done. If discontinuous, it is discontinuous, then you have to identify, is it infinite, jump, removable? You already know. Because we looked at the graph, it should be infinite. So we say infinite discontinuity. So in case there's no graphing available, you can do around the 1, x value as a 0.9, 0.99, 0.999, x value from the right, and plug x value to the function. You get the y value. Look at the y value. Here, the y value used to be minus 10. It's minus 100, minus that. So you know it's decreasing big time, so fast. Same thing, 10, 100, 1,000. So it's increasing huge. So that's numerically showing, yeah, this is a scenario. Okay? So it was discontinuous. What kind of discontinuous? Infinite discontinuity at x equal to 1. Okay, B. Determine whether this function is a continuous at 2. What would you do? Graph it. Graph it using calculator or software. This is a graph. X equal to 2. X equal to 2 is right here. For me, it looks nice curve. I don't see anything discontinuous, so I'm 90% positive. Yes, continuous at 2 because it looks nice to me. Do you remember there's a special case? You have to be careful. So what do? You plug it in 2 for value of x. 2 minus 2 is a 0 numerator. Good morning, everyone. So we'll start doing content learning starting from this week. So I don't know how many of you have watched my instruction video. Let me. Okay, going back. Just a second. Okay, sorry for that. Shh. Snowballs? Shush. Okay. So where were we? So you do plug it in 0 for x. You got numerator 0. You do plug in 0 for bottom x. 2 squared becomes a 4. 4 minus 4 becomes a 0. 0 as a denominator is no good. 0 numerator is okay, but 0 in denominator, no good. What do I mean by no good? It's undefined, busted. So even though when you look at the graph, it looks nice curve, it looks everything fine, it looks like just like a continuous everywhere x equal to 2, graph cannot show you a whole. Okay, so it looks curved, nice curve, all continuous. You are tempted to say continuous at x equal to 2. When you check by plugging in x equal to 2 to the equation, denominator becomes 0, so you should know it's not continuous. It's a discontinuous at x equal to 2. Okay? So if you come back to the graph, you might say, well, how does it look nice continuous here? Because your graph calculator or software cannot show you a hole. So to be precise, there should be a bigger hole there at x equal to 2, which your calculator cannot present. So that's something you have to check by hand. So as you can see by now, you should know what kind of discontinuity. It should be this one. The one with the hole is a removable discontinuity. Okay? Well, I'm asking you to use a continuity test. So you have to do condition 1, 2, 3, and all that. 1 we already did it. We plug it in, f of 2, plug it in 2 for value of x, and it was undefined. So condition 1 busted. So continuity test, done deal right there. Condition 1 is undefined. So f of 2 does not exist. So done deal. Discontinuous. If discontinuous, identify the type of infinite jump removable. We talked about it. It has a hole, it's removable. So if you look at the number analysis here, so we are picking x value close to 2 from the left, we're picking x value close to 2 from the right, and look at the y value approaching. It's approaching to 0.25. So approach to 0.25. What does that mean? Yeah, so it's y value is approaching 0.25, y value is approaching 0.25. So you know it's approaching to same value, not like one goes like 1,000, the other one goes minus 1,000. That's infinite discontinuity. This is a removable discontinuity because they're approaching to same value, which is so easy when you look at the graph. So continuous, discontinuous at 2. What kind of discontinuity? Removable discontinuity. Okay, pause the video. You try this, please. So if you try this, graph it using graphing calculator, you should be able to tell it's infinite discontinuity. At x equal to 1, check it. Okay, intermediate value theorem. So it says for f of x continuous function, a is less than b. So value of x, a is here, b is here. And there is a value of n such that n is between f of a, f of b. Between f of a, f of b, there's n value. Then there gotta be c between a and b, which is satisfying this. Sounds awfully complicated, right? So what are they talking about here? So basically, this is what they're talking about. There's a value, there's a b value for x. If you have a function, you might have a line, you might have a curve. They are saying for value of x of a, there's a function value of f of a, meaning there's a point here. For function value of x as a b, there's a function value of f of b, which means all they are saying there's another point there. And they say this function is a continuous, meaning it's all connected nicely. That's what I mean by continuous. And this is what they're saying. If you choose a number on y-axis between a and b somewhere, there gotta be matching value on x on that function. That x value has to be between a and b. What are they talking about? So all they are saying is somehow if this is a continuous, this cannot happen. So for n value of whatever that is, so if you have like this gap, there wouldn't be anything matching here. So they are saying that's not possible. If it's a continuous, it has to be somehow connected. That means whatever n value is, there gotta be matching value of c, which has to be between a and b. That's all they're saying. So you might say, okay, so what does that have to do with us? They have a corollary about that. They can apply that with finding zero, which is x-intercept. Super simple. So if I say, there's an x-axis, let's say. If you have a point on the below of x-axis, let's say the point above x-axis, and if the function is continuous, there gotta be x-intercept between these 2 points. Because continue, you have to somehow connect them. So wherever that is, you have to pass x-axis at least once. Can you pass more than once? That's possible. But all I'm saying is, between these 2 points, you have to have x-intercept at least one between these 2 points, because you have to connect them somehow. Does that make sense to you? So what does that mean? If y value is negative, y value is positive here, there gotta be zero between. What is zero? X-intercept. The graph has to pass x-axis somewhere. That's what they're saying here. Okay. Determine between which consecutive integers is a real zeros of this function located in the interval -2 to 2. So what are you supposed to do? Given table, you are supposed to tell me what integer to what integer we have a zero, which is x-intercept. So look at the y value. Positive, positive, negative. Y value is positive. Y value change sign to negative between these 2 points. So right here is where the zero is. Positive to negative. Just like this example. You remember here. So I can change that to a positive, negative. So this value, -1, so it's a positive value here. 0, x equal to 0, y value is negative. So that's what? X value is -1, x value is 0. So you have to have a function like that, meaning there gotta be x-intercept between -1 and 0. That's all they're saying. -1 and 0, there gotta be 0 between. Now keep going. Minus to minus, nothing happens. Minus to plus, right here. Between 1 and 2, there gotta be 0. So what's the answer? Between -1 and 0, between 1 and 2. Okay? You can also say between -1 and 0, between 1 and 2, or use this, or use interval notation between -1 and 0, between 1 and 2, whatever is easier. You, Alex, I think you might ask this interval notation between this, between this. It's a lot easier if you have graphing right in front of you. It's no-brainer right there. Between -1 and 0, there's a 0. Between -1 and 0, between 1 and 2, okay? Just by looking at the graph, that's even easier. But I have to ask you to try without looking graph, just by looking at the table. You try, please. Right here, y value to y value, minus to positive. Right here is the positive, positive, positive. Then everything is positive. You change sign for y, minus to positive right here. So what's the answer? Between -2, between -2 and -1 should be the answer. Between -2 and -1. And if you happen to graph here, well, that's even easier. -2 to -1. So between -2 and -1, that's where the zeros are. Done. Okay, limit at infinity describe the end behavior of a function. Okay, end behavior means as you move to the right, as you move to the right, as you move to the right, what happened to the y? Increases. As you move to the left, as you move to the left, what happened to the y? Decreases. That's what I mean by end behavior. You learned that from algebra 1, you learned that from algebra 2. Use the graph to describe its end behavior. Okay, very simple. So I will say, as you move to the left, as you move to the left, very left, as you move to the left, as you move to the, as you go to, as x go to the left, what happened to the y? Y is decreasing, right? Y is decreasing. So y decreases. Y decreases. Okay, as you go to the right, as you go to the right, what happened to the y? Y increases. As x approaches to right, y increases. That is end behavior. End behavior. Okay, algebra 2. Algebra 2. This is how you roll in algebra 2. As x approaches to left, which is minus infinity, y approaches to decrease means minus infinity. As x approaches to right, that's as x approaches to right. Right means positive infinity. Y approach to increase means going up. That means positive infinity. This is how you wrote in algebra 2. Okay, in pre-calculus, you are using this limit notation. So this is how you write left limit of f of x as x approaches to minus infinity equal to, that's what this goes, minus infinity. So this answer goes here. So that's exactly the same here. So as x approaches to infinity, y approaches to infinity, how do you write that? Limit of f of x as x approaches to infinity equal to whatever that is, you're writing here, which is infinity. So it's very important for you to know how to write this. So all this, what does it say? As x approaches to the left, as x approaches to the left, then you have to answer this. What are these? As x approaches to the right, what happened to the y? Okay. So that is the answer for this. You do it. Pause the video, you do it. So end the video. As you go to the left, as you go to the left, what happened to the y? Decreases. So this is what we mean by as you go to the left, decreases. So minus infinity. As you go to the right, what happened to the y? Increases. Okay, you have to be careful. This doesn't change. Look at it. This doesn't change. Only changes this. What value goes here? What value goes here? Okay. Well, before we go to a different question, because you had exactly similar style, I'm not just. What if you had a question like this? I gave you this, and I say find end behavior. Then how would you do it? So this is what you do. Limit of f of x as x approaches to minus infinity. That's left side limit. Limit of f of x as x approaches to positive infinity. That's right hand side limit. So left hand, this is an as x approaches to minus infinity. As you go to the left, what happens to the y? Minus infinity. So you write minus infinity. This means as you go to the right hand, what happens to the y? Minus infinity, you write minus infinity. That's how you write the answer. Okay, so I need you to understand this is left hand. As you go to the left, what happens to the y? Write it down. This is a right end. As you go to the right, what happened to the y? You write it down. Same thing, end behavior. Okay, so if you keep going to the left, keep going to the right, keep going to the left, watch end behavior. Someone says, well, it's keep decreasing. So you have to be a little careful here. So this like, oh yeah, it's keep decreasing, minus infinity. Actually, it's not. So this case, when it keeps going to the left, it's actually approaching to 0. You keep going to the right, it's actually approaching to 0. So for that, you might want to play with the calculator. So if I were you, I'll plug it in x value as like minus 10,000. X value is minus 10,000. Plug in x value, use your calculator. Then y value will be almost 0. Same thing. Plug it in x value as 10,000. Y value will be almost 0. Okay? So this case, you have to be careful. If the graph is like shooting down, straight down like that, shooting up, straight up like that, then no question. It's infinity and infinity. But it goes like this, then there's a possibility there's a horizontal asymptote. Okay, so you have to check that. So if you do that, you get, if you keep going to the left, 0. If you keep going to the right, approach to 0. Okay? Another way for you to tell end behavior, you can only use it for end behavior, is power of x. If you compare power of x on numerator, power of x and denominator, and if denominator x has a higher power than numerator, end behavior will be always 0, left and right. So x squared has a second power, x on numerator is only first power. It doesn't matter. End behavior for both will be 0 and 0, both sided. 0 and 0. Okay, use the graph to describe end behavior. Again, graph it. Don't make a mistake of saying, as you go to the left, it keeps going down minus infinity. As you go to the right, it keeps going up positive. Don't make that mistake. Okay, it's kind of increasing, but gradually you have to think maybe there's a horizontal asymptote. So how would you tell that? Well, one way is you plug in x value as a very small value, like minus 10,000. Plug x value as minus 10,000. Plug x value as minus 10,000. Then you will get very, very close value to 2/3, which is 0.66666. You can also plug it in x value as very high value, such as 10,000. Plug in 10,000, calculate using calculator. You'll get y value as like 0.6666, which is 2/3. Okay? So end behavior, when the curve goes like gradually like this, so be careful. You want to check by plugging x value is very small value, very high value. Then that's one way to do it. Okay, using calculator. This one, do you remember previous shortcut? I told you you can compare highest value, highest power of x, numerator, denominator. So let's look at x power here. X doesn't have a power, which means it's a first power. Denominator has x, which is a first power too. So does denominator have a higher power of x than numerator? No, they should have a same power. First power, same power. Then coefficient of a coefficient of x. So nothing matters. Just 2/3 becomes answer. 2/3. Again, this is kind of shortcut. You didn't follow what I just did, forget it. Just plug it in x equal to minus 10,000. Just plug in x equal to 10,000. Then you will get that value. Just don't get confused with end behavior, which is so obvious. Things like this, you don't need to check minus 10,000, 10,000. I mean, there's nothing wrong with checking in, but this is shooting down, shooting up like that. You can just say it keeps going down, keeps going up, minus infinity, infinity. That's an easy call. You only check minus 10,000, 10,000 if the graph is kind of flat. Okay? Okay, guys, make sure you finish your Alex homework.